Hi, in this video we are going to discuss about the bipolar cascode. So we have the bipolar cascode as a current source. Or a current sink. Okay, so an ideal current source is supposed to behave this way. So the current I1 is provided by the voltage V1, but the value of I1 does not depend on the value of V1. So it will make a lot of sense if I get this graph. So I have I1, which is supposed to remain constant, and V1. So regardless of the value of V1, the value of R1 should remain constant. Of course, V1 should be large enough to produce I1, else there will be no I1 in the first place. Okay, so we've already studied the transistor as a voltage controlled current source, where the voltage somewhere else controls the value of I1. So here we are going to look at how to get the bipolar as a current source, and we'll look at what is meant by cascode current source, how we can make the bipolar a better current source. Okay, so from our basics, we know the relationship between the collector current IC and the VCE. So we know once the VCE is enough to reverse bias the collector base junction, so you have a BJT. So once the VCE is enough to put this junction in the reverse bias, then the device will be in forward active region, if of course the base emitter junction is always also forward bias. So assuming at this point the voltage at the collector is greater than the voltage, is more positive than the voltage at the base, then it means we should have a current source behavior. And of course before that we have this sort of behavior here. We also learned that due to early effect, this is what actually happens. Early voltage effect. Okay, so how do we improve on this? So this is an ideal current, so what we expect, but this is what we are getting. Okay, sorry. Okay, so just hope didn't have to end the video. Yes, I didn't have to end it. Okay, so this is what we are getting. So how do we improve upon this? We can add degeneration to the emitter, and that increases the output impedance. So adding RE here will increase the output impedance, and if the output impedance increases, because the ideal current source has an impedance of infinity, so if the output impedance increases, then this slope here will be gradually looking at this. So in adding emitter degeneration, R out seen through from the collector becomes 1 plus the intrinsic gain GMRO, let's call this transistor 1, times RE in parallel with R pi plus RO1. Okay, so we notice two things here. We can increase the output impedance by increasing the value of the emitter's resistor. But what happens when we increase the output of the emitter's resistor? Let's pay attention here. Now, increasing the value of RE means that the emitter voltage rises, and once the emitter voltage rises, then the base voltage, if not increased, the device cannot be in the forward active mode, because the base emitter voltage should be such that the base voltage should be at least something around 0.5 more than the emitter voltage. Ideally, sometimes you say 0.7, but 0.5, 0.6 is okay. 0.8. Okay, so if we raise, so assuming initially the base voltage was 0.7 volts, the collector voltage had to be 0.7 and above. We can look at soft saturation, but let's not just go into that yet. Let's just look at it's being more positive. So let me just put 0.8 here for easy understanding. Okay, so now when the emitter resistance increases, then means the voltage at the emitter should also increase. And when the voltage of the emitter increases, we have let's say I increase the value of the resistance, so the emitter's voltage rises to, let's say, 0.3 volts, which means the base voltage should be raised to at least 1.0 to have the base emitter voltage to be still 0.7. That's what we decide, depending on the current that we want here. So the base voltage has now risen to 0. So let me make sure it's clear. So we are talking about three things here: emitter voltage, the base voltage, and the collector voltage. Alright, so the emitter voltage has risen because I increased RE in an attempt to raise the output impedance. I raised the emitter resistance, so the emitter voltage raised by 0.3 volts. That means if I don't raise the base voltage by 0.3 volts, I'm going to lose the base emitter voltage. So if the base voltage remains on 0.7, then the base emitter voltage will now be 0.4. So if I want to maintain the base emitter voltage, then I have to raise the base voltage to 1.0 volts. Okay, So previously the collector voltage was on 0.8, which made the base collector junction reverse biased. So it means my current source would behave like this. Up to 0.8, that's when the device goes into forward active region and I get my straight line. Before 0.8, the device cannot behave as a current source. Of course, we know there's early voltage too, but assuming I've been able to reduce the slope because of my emitter degeneration resistance. Now I further increase the emitter degeneration resistance, and the scenario here comes into play. Increases the RE's value. VE, the voltage at the emitter, will raise because it's just current IE passing through RE to raise the voltage of VE. You can just assume IE and IC are approximately the same. Okay, then we have to raise the base voltage as already explained. Now guess what? 0.8 will no longer keep the device in forward active. So you have to also raise the voltage here by 0.3 to 1.1, which means that now my device is going to look like this. At 1.1 VCE, voltage at the collector point, that is when my device will start behaving like a proper current source. So gradually I'm deviating from the ideal current source, which should be like this. I'm getting the slope, but I'm losing this part of the current source behavior. So that is why using an emitter degeneration resistor is not ideal. So this introduces us to a cascode. So for the cascode current source, we replace the emitter with another transistor. So Q1, Q2, and we call this the Cascode transistor, and we call this the degeneration transistor. So in the next video we will go into details, and in the same or next video after that we look at some LT spice simulations. Thank you.